Hello friends, today we will consider the mechanism of nucleophilic substitution reactions. There are two types of reactions commonly known by the names Sn1 and Sn2 reactions. Sn1 means substitution nucleophilic unimolecular and Sn2 is substitution nucleophilic bimolecular reactions here. Okay, now you see the overall reaction, a nucleophilic substitution reaction, we can see that is at an sp3 hybridized carbon atom. It will involve two sigma bonds. That is the overall reaction. We can represent it in this fashion, that is Rx. Okay, now Rx, R is an alkyl group here. Okay, now this is reacting with a nucleophile. So nucleophile, commonly it is represented like this. Okay, this is giving you RNU plus X minus. This is the overall nucleophilic substitution reaction. We can represent it in this fashion. That is X. It is replaced by X is a electronegative atom, more electronegative than carbon atom. R is an alkyl group. So here it is a CX bond is there. Okay. Now this CX bond, it is sigma bond here. This sigma bond, CX sigma bond, it is broken here, and a new sigma bond here, that is CNU. New bond, it is formed here. Okay, this is nucleophilic substitution reaction. So the carbon atom, it is an sp3 hybridized carbon atom here. Two sigma bonds are involved here. Okay, now the bond to the carbon bond with the leaving group, it is broken, and a new bond, carbon with the nucleophile, it is formed here. Now, to understand the mechanism, how this reaction takes place, that is the pathway of this reaction, that is the mechanism of this reaction. To understand it, we have to see the timing. So now here the bond is broken, one bond is broken, one bond is formed here. So what happens first, whether these two events are taking place simultaneously. That is one thing, or one is taking place before the other one. All these things are to be examined to arrive at a proper mechanism of the reaction here. Correct? So now to understand the mechanism of the reactions, now we must know the timing of these two events here. So what is the order of the bond breaking, and what is the order of the bond making here? Okay, there are three possibilities. We can visualize three possibilities here. The first possibility will be, okay, the bond breaking and the bond making. Okay, they take place at the same time. That is the carbon X. Okay, the leaving group. The bond, between the carbon and the leaving group, that is the bond, sigma bond, that is broken, then a new bond is formed here. So this bond breaking and bond making, they occur at the same time. So that is one possibility here. Therefore, it will be a one-step mechanism here. So we can represent it briefly like this. This is our nucleophile here. So this nucleophile, it will be reacting with so this is our leaving group here, X. So this will depart with the electron pair in the bond here. So we will be getting the molecule in this fashion here. Okay, Nu. Then we have X minus, that is the leaving group here. Correct? Now, this is the simultaneous activity, that is bond breaking and bond making take place simultaneously, that is at the same time here. Therefore, this will be the rate of the reaction here. It will be rate is equal to, that is K. That means this is all been studied by kinetic studies here. Okay, rate will be Rx and Nu. That is, it is a bimolecular reaction. So the rate of the reaction depends upon the concentrations of both the reactants here. Important point. It is a one-step mechanism. That is, the bond breaking and bond making take place simultaneously. Therefore, it is a one-step mechanism. Correct? Therefore, now the rate of the reaction, okay, it will depend upon the concentrations of both the reactants. That is the alkyl halide here. Rx is the alkyl halide, R is the alkyl group here, and the concentration of the alkyl halide and the concentration of the nucleophile here. Therefore, it is a second order rate equation. Okay, bimolecular second order kinetics here. Important points here. this kind of reactants. Okay, it's a one-step mechanism, and bond breaking and making take place simultaneously. There is a bimolecular reaction, two molecules are involved here. Rate depends upon the concentrations of the both the reactants here. Second order kinetics. So this is one possibility here. Now the second possibility we can identify, that is the bond breaking occurs before bond making. That will be a two-step mechanism here. Let us see how the the second mechanism will be, that is C. So this is our bond here, CX bond. This is breaking here. This bond is broken. So now this is giving you an intermediate here. That's a this is a two-step mechanism. The earlier one is only a one-step, single step, it is getting over. Now we are getting an intermediate here. This is a carbocation intermediate. Reaction intermediate or reactive intermediate, whatever call it, So this is the leaving group here. So this will be reacting with the nucleophile here. Okay, so this will be, we'll be getting this molecule here. So this is a new bond here. This new bond, and this bond is broken here. CX bond is broken and a CNU bond is formed here. Okay, now this is two-step mechanism. That is, it is taking place in two steps. So see, this is step 1 here. Step 1, the leaving group is departing with the electron pair in the bond, and we are getting a carbocation reactive intermediate here. And in the second step, the carbocation intermediate, it is reacting with the nucleophile to form the carbon NU, CNU bond here. Okay, now here the rate of the, there are two steps involved. Now rate, again, the rate of the reaction, it is equal to K into Rx. That is alkyl halide, the concentration, okay, of the reactant. Only one reactant is, we are concerned with only one reactant here. The rate depends upon the concentration of only one reactant. Therefore, it is a first order kinetics. First order kinetics. Then it is a unimolecular. Okay, the first step here, step 1, where the bond is, bond cleavage take place or bond breaking takes place here. That is the rate determining step. First order kinetics, the first step, it is the rate determining step. That is the slowest step. Okay, so rate determining step means we have to supply energy. Here, energy of activation, EA, we have seen that in our previous class, correct? So the first step here, where the bond breaking is involved, that is a rate determining step here. So the rate here, it depends upon the concentration of only Rx. Therefore, it is a first order kinetics and unimolecular. Okay, so these are the two main, two options here. That is a carbocation intermediate. The first step, it is a rate determining step here. Okay, rate depends upon the concentration of Rx, the alkyl halide here. Okay, it is a first order kinetics here, unimolecular reaction here. Now, the third possibility, for argument's sake, okay, you can ask me, now in this case, the bond breaking occurs before bond making. You will ask me, why can't it be the other way around? The first the bond making can take place and later on the bond breaking can take place. Okay, for argument's sake, let us examine how this reaction will be. Okay, the mechanism we can just see how it will look like. That is, in a reaction of this nature, bond making, it occurs first before bond breaking. So in that case, again, it is a two-step mechanism, correct? So this is the leaving group here. It will go. Now here we have the nucleophile. Okay, now we will be getting an intermediate. So what is the nature of this intermediate here? So this is Nu, then we have X here. So here minus charge, negative charge here. So this will be giving you the final molecule here, Nu plus X minus, the leaving group here. Okay, now we are assuming that the making of the bond, that the CNU bond, it forms first and the CX bond is broken second, subsequently, correct? So this bond, the mechanism, it will have two-step, is a two-step mechanism. This is the third possibility. Okay, two-step mechanism. and there is an intermediate. So look at this intermediate. Okay, negative charge. A negatively charged carbon atom is here. How many electrons around that carbon? There will be 10 electrons here. So this carbon is having 10 electrons around it. So is it possible? Because 10 electrons is not a possibility here. Because as per the fundamental rules, we should have an octet. Maximum 8 electrons. Correct? Around the second row element of the periodic table, as you know, you have seen maximum 8 electrons. That is an octet formation. Therefore, this mechanism, it is violating the fundamental principle. Inherent defect in the mechanism here. Inherent problem in the mechanism here. So it contradicts the fundamental rule. That is the 10 electrons around this carbon, negatively charged carbon here. That is against the octet principle. Therefore, this mechanism will not sustain. Okay, this is not practical. Therefore, this can be disregarded. We should not consider this third mechanism here. Therefore, the point here, what we are going to make, that is there second, in a nucleophilic substitution reaction, there can be two mechanisms only. So first one is a one-step mechanism where the bond breaking and bond making take place simultaneously. And the second mechanism, it is a two-step mechanism. So two-step mechanism, we are getting a carbocation intermediate here. Two mechanisms for a nucleophilic substitution reaction here. Okay, now we can elucidate it from the kinetic data. Okay, now because this mechanism has been elucidated from the kinetic data, so we are using two different types of alkyl halides here. Okay, so these two different types of alkyl halides, it will be reacting with the nucleophiles. Okay, that is, reaction between two different types of alkyl halides here. That is two different types of alkyl halides. We can say this is RX kind of a thing. Then we can have, say, R3X. Like this, two different types. We can have nucleophilic substitution reaction. We can say so. Let us consider the reaction. Say bromomethane, for example, with an acetate anion. I will change this page. So this first reaction we are going to consider is CH3Br. Okay, this is bromomethane here. This bromomethane, that is the substrate here. Then it will be reacting with the acetate anion here. Okay, this is the nucleophile here. That is bromomethane reacting with acetate anion here. So what will be the product form here? Let us see. So CH3Br, it will be reacting with the acetate anion. Then C double bond O, CH3. Okay, this is acetate anion here. This is bromomethane. So this is the first reaction we are considering here. Okay, so this will be giving you CH3, that is acetate here, methyl acetate, CH3O, CH3. Okay, this is a leaving group here, Br minus. So methyl acetate is formed here. Now here the kinetic data, it has indicated the reaction rate as follows here. So rate of the reaction, it is equal to K, that is the rate constant, into CH3Br, that is the concentration of the alkyl halide here, and acetate anion. Okay, so reaction rate, it depends upon the concentration of the two reactants here, that is acetyl anion and methyl bromide, or the or bromomethane here. Okay. So the rate depends upon the concentration of both the reactants here. Okay. So in the equation, rate equation, the concentrations of two reactants, that is the nucleophile as well as the substrates, it is figuring here. Therefore, what is the order of the reaction here? The kinetics, it is a second order kinetics. Second order kinetics, then it will be bimolecular reaction. bimolecular reaction here. How many steps are here? Okay, only one step. Okay, one step mechanism. So this kind of reaction, this is the nucleophilic substitution. Okay, substitution, nucleophilic substitution. It is a bimolecular reaction here. So this is known as Sn2 mechanism here. That is substitution nucleophilic bimolecular. Second order kinetics, one step mechanism, bimolecular. The rate depends upon the concentrations of both the reactants. That is the alkyl halide as well as the acetate anion here. Okay, now 2 here. Sn2, this 2 refers to the kinetic order of the reaction. That is, it is a second order reaction here. Nucleophilic substitution at a sp3 hybridized carbon atom. So this is one mechanism, Sn2 mechanism here. So this is one type of alkyl halide we have seen now. Now the second type of alkyl halide, let us see. Because the same nucleophile we are using here, acetate anion we will be using here. So a similar nucleophilic substitution reaction, say with this compound, that is CH3 thrice, we can say CBr. So this compound, and this, this also will lead to a substitution of the bromide anion here. This bromide, it will be substituted by acetate anion here. Acetate anion here. So the kinetic data here also, it has suggested that this reaction rate, it will depend upon the concentrations of only one reactant. Okay, that is the kinetic data. So the rate, of the kinetic data shows that the reaction rate here, the rate of the reaction depends upon the concentration of only one reactant here. That is the alkyl halide. Okay, so rate equation, that is a first order kinetics here. Okay, and a two-step mechanism in which the rate determining step, it will involve the alkyl halide only. So this bond breaking here, okay. So the reaction will be CH3 thrice CBr. Then we have the acetate anion here. CH3. Okay, so this is giving you this compound. Then C will be there. O. CH3. Then Br minus. Correct? So this is the compound or the molecule being formed here. CH3 thrice CO CH3 Br minus. So here we have seen the rate of the reaction. From the kinetic data we have seen the rate of the reaction, it is equal to the concentration of this alkyl halide only. Okay, this is the thing here. Okay, kinetic data shows the reaction rate, it depends upon the concentration of only one reactant, that is the alkyl halide. The rate equation, it is a first order. The kinetics, it is a first order kinetics here. So this is a first order kinetics here. It's a two-step mechanism here. Two-step mechanism. Okay. Now only one reactant appears in the rate equation here. First order kinetics. Then we can say this is a two-step mechanism in which the rate determining step. There is a rate determining step, that is the involving the alkyl halide here. That is a bond breaking here. Therefore, the transition state, there will be two transition states here, two energy barriers and all this kind of a thing. Okay, we are not going into the details now. So these are then the two different mechanisms here. So this mechanism in equation this equation here, whatever we have seen here, it is known as Sn1. Sn1 means substitution nucleophilic unimolecular. Okay, this is an introduction to both the kind of mechanisms here, that is Sn1 and Sn2 reactions here. Now let us examine Sn2 in detail now. In this class we will be focusing more on Sn2 mechanisms only. So next class we will see Sn1 in detail here. Okay, now general features of, what are the general features of Sn2 mechanism? It's an important thing. See, the general features of Sn2 mechanism. First thing is the kinetics here. So we have seen it's a second order kinetics. Sn2, second order kinetics. So reaction is a bimolecular reaction. We have seen that. Now, if you see change the concentration here. So let us see what will the rate of the reaction, how it is dependent upon the concentration of the reactants here. That is, we have seen bromomethane, we have seen, and this acetate anion here, Ca3CO minus. Okay, so the rate is dependent upon the concentrations of both these reactants here. Okay, so it's a only one step is involved here. We know that bond breaking and bond making, they occur at the same time here. Correct. Now, if we change the concentration, okay, so the bromomethane concentration I am changing. What will happen to the rate of the reaction here? So changing the concentration of either reactant, only one reactant we are changing at a time. That means the rate of the reaction, it will double. Okay, if we change the concentration of the bromomethane, the rate of the reaction will double here. Now, if we change the concentrations of bromomethane and acetate anion, both the reactants here, the rate will become fourfold. Got the point? So changing the concentration of either reactants, it will affect the rate of the reaction here. So now if we double the concentration of either the nucleophile or the substrate or the alkyl halide here, it will double the rate here. Now if we double the concentrations of both the alkyl halide and the nucleophile here, the rate of the reaction, it will become fourfold. That is most important point here. Now the energy diagram, we can draw an energy diagram for this kind of a Sn2 mechanism. This reaction we can draw an energy diagram. How will you draw that? Energy diagram, say two coordinates, y coordinate and x coordinate. So y coordinate will be plotting the energy and x coordinate will be plotting, that will be the reaction coordinate. So roughly I am just showing you. So this is the like this. It should have been a straight line, but unfortunately it is not getting into a straight line here. Let us see if it is becoming okay. Yeah. Now this is the reaction coordinate. Okay, reaction coordinate here, and this side we will be plotting energy. That is our activation energy and all we can see here now. Yeah, now it has come out more or less all right now. So roughly you can follow. Okay, here we'll be plotting energy. Correct. Now what will be the nature of the energy diagram here? It's a one-step mechanism. There will be only one energy barrier. The transition state, it will be only one transition state here. Okay, so here we have the reactants. Assuming this is the point here, that is the bromomethane. Bromomethane plus acetate anion here. Okay, so this is the energy level here of the reactants here. So This is going up like this. It will come down like this. You see here, this is the products here. Here the product will be CH3 acetate plus leaving group, bromide. Correct. So this is the kind of energy diagram here. That is, the products are at a lower energy here. So the equilibrium will favor the formation of the products here. Correct. The products are at a lower energy than the starting materials. Therefore, the equilibrium favors the product, the formation of the products here. Okay. Now this is our energy of the reactants here. Okay. Now if the energy of the reactants, so this is our activation energy. That is, activation energy is the energy difference between the starting material and the transition state here. This is the activation energy here. Okay. Now this is the energy level of the products here. So this is our enthalpy change. Okay, delta H. That is the heat of reaction here. So this is the transition state here. That is the energy barrier. Since it's a one-step mechanism, there is only one energy barrier here. Okay, transition state here. So how will you represent the transition state? In the transition state, the carbon Br bond is partially broken and the carbon oxygen bond is partially formed here. Okay, and each one, that is the Br and the oxygen here, it will be bearing a partial negative charge. What's the point? That is, in the transition state, the carbon Br bond, it is partially broken. First point. The second point is, and the carbon bond, it is partially formed here. Okay. Now the attacking nucleophile and the leaving group, it will bear a partial negative charge. That is the bromine and oxygen. It will be bearing a partial negative charge here. So how will you represent the transition state here? The transition state will be CH3, then we can say CO, then we have oxygen here, then partially this bond is formed here. We can draw hydrogen, CH3. Correct? Then we have bromine. That I am putting a dotted line here, dashes here. So this oxygen will bear a positive, negative charge, partial negative charge, and this bromine will bear a partial negative charge here. So this is our transition state here. Okay. So transition state for a one-step mechanism. It's a double dagger we are putting here. So CH3COO, there is a dotted line we have put it here, dashes here, that will indicate a partial double bond character here. Okay, transition, partially the bond is formed here and not double bond here character. The CBr bond is partially broken and the CO bond is partially formed here. There is a partial bond here. It is not fully formed or it is not fully broken. Correct? That is what is meant by partial. That is, it is not bond breaking and bond formation. It has not taken place fully here in the transition state here. Okay. So the transition state is something that is the energy barrier. It is to be overcome for the reactants to proceed to become the products here. Okay. Here now we have seen that is the products are at a lower energy here and therefore the reaction favors the formation of the products here. Correct. So this is the energy diagram. Energy diagram for an Sn2 mechanism, Sn2 reaction. Sn2 reaction, one-step reaction. Correct? One-step mechanism here. This is the energy diagram for a Sn2 reaction, one-step mechanism here. Correct? Now, let us see now the stereochemistry. That will be very interesting. I will be telling you what is meant by Walden inversion. It's a new concept here. The stereochemistry of Sn2 mechanism here. So Sn2 reactions, the stereochemistry, how it will be there. Stereochemistry means, there should be a stereogenic center to understand these reactions, there should be a stereogenic center. Stereogenic center means asymmetric carbon. That is 4 different groups attached to a carbon atom here. Correct. Now, there are 2 possibilities. You see, in the nucleophilic substitution reaction here, that is a leaving group and a nucleophile here, there are 2 possibilities of attack. Okay, the nucleophile can attack from the front or the nucleophile can attack from the back. Okay, what does it mean here? That is, one is the front side attack. Front side attack. And other one is a back side attack. Okay, these 2 possibilities are there here. That is, suppose we are having, this is the Rx here. So this nucleophile here, it can attack from here. That is one possibility here. And take away this, the bromine can leave. Correct. And we can get this RNU bond like this here. Plus X minus. This is one possibility. Okay. And the other possibility, that is attacking from the front side. Directly it is coming and hitting. Okay. The other possibility will be from behind it is attacking here. Like this. Okay. This attack will be from this side here. Therefore, this product formed will be like this. That is all. This is the only difference here. That is, one is the, there is an inversion of configuration here. Configuration will get inverted. That is, front side attack, we can say the nucleophile, it will be approaching, okay, from the same side as the leaving group here. Okay, we have the nucleophile, we have the leaving group. Okay, so the nucleophile is approaching from the same side of the leaving group. Now, backside attack, backside attack means the nucleophile, it is approaching from the side opposite to the leaving group. That is behind the, that is why it is known as backside attack. That is from the side opposite to the leaving group. Attack is from the opposite side here. Correct. So now let us consider the reaction here. What will be the nature of the reaction here? So we will consider a compound like this, say methyl group, say an asymmetric center here. So we can consider, say, hydrogen, then we can see another group here, we can say bromine, then we can put a deuterium, isotope of hydrogen. Okay, so this is an asymmetric center here. Okay, this, and this is reacting with a nucleophile. Okay, so let us analyze here. Here, now the leaving group here, bromine, is a leaving group. It is bonded to a carbon atom, which is a stereogenic center. That is an asymmetric carbon bonded to 4 different groups here. Okay, now let us see the structural difference here. When the nucleophile attack from 2 directions. Now I will just draw it here. I will just change this page. It will be interesting for you. So this is leading to the concept of Walden inversion. It's an important point here. That is, we will see the front side attack. Two different types of attacks here. Now we have this carbon here. This is the carbon here. Now this is our leaving group here. Correct. Displacement we can show like this here. Now we have this hydrogen. Then we were telling deuterium. D here. Then on a wedge we can show the methyl group here. Correct. So like this, now this nucleophile is approaching from the same direction of the leaving group here. Same side, that is right side, I have put it right side here. And this is the left side here. Okay, now if you take it, what is the nature of the product here? Now same thing, the nucleophile will replace or substitute the bromine from the same side here. There is other groups are all intact. There is no change here. Okay, now the methyl group on the wedge, it remains like this, and your deuterium, it remains like this. Okay, and Br minus. This is the one way, one possibility, that is the front side attack by the nucleophile on a stereogenic center. That is the leaving group, it is attached to a stereogenic center here, an asymmetric carbon here. Correct. Now what happens here? So this is, say, configuration A. This configuration, it is retained. Retention of configuration, it is known as. So the leaving group, it is drawn on the right side. Okay, so the nucleophile attack, it is taking place on the right side, that is from the same side. Correct. Now all other groups, they remain in their original position. There is no change here. Correct. Now this is called front side attack. So the front side attack, it will result, there is no change in the configuration. That is retention of configuration. Correct. Around the stereogenic center. That is the attack here. That is front side attack here. Now if you see, the back side attack now. That is, nucleophile is approaching from the side opposite to the leaving group here. Nucleophile approaches from the opposite side to the leaving group. So what will be the nature of the configuration here? The structural difference we will have to see. Backside attack. So in the same way, we can draw the same compound here. CBr we can have. Then we will have our hydrogen behind the plane here. So this methyl will be putting on a wedge. Correct. Then we have the D here, deuterium here. So now what happens here? Bromine leaves from this side and this nucleophile, it is attacking from this side here. Correct. So this will go, this nucleophile, this lone pair here, it will come to this electrophilic center. Correct. Now what is the compound formed here? This nucleophile will come here, this side, left side here. Okay, originally it was the bromine is here, right side here, just opposite to the bromine, the nucleophile is getting attached here. Correct. Rest of the things are all changed this side. Okay, now the CH3, it is here. Then here we have the deuterium here. Then we have this hydrogen here. Okay. So this is the compound being formed here. So the configuration, it is getting inverted. Br minus here. This is configuration B. There is inversion of configuration. Okay. So correct here. Okay. So the leaving group, it is on the right side here, and the nucleophile is attacking from the left side here. Okay, the nucleophile and the leaving group, okay, they are in the opposite position. So it will, in relation to the other groups here. Okay, we are always considering it in relation to the other groups here. Opposite directions here. Okay, so backside attack, this is a backside attack of the nucleophile. It results in inversion of configuration at the stereogenic center here. Okay, we have the stereogenic center. So the configuration is getting inverted here. That is, backside attack always results in the inversion of configuration at the stereogenic center here. Okay, now here A and B. So which is A here? This is the A. Okay, now let us see A and B here. What is the relationship between A and B? A and B are enantiomers. There are two different compounds here. A and B are enantiomers. That is non-superimposable mirror images. Correct. This relationship here. A and B are different compounds. Okay. Now they are stereoisomers. They are non-superimposable mirror images here. Correct. Now in Sn2 reactions, what we have seen, that is only the product B. It is favored. That is the product B is formed. That means a backside attack. It only takes place here. Backside attack. Only backside attack in Sn2 reactions. Mechanism. Important point here. That is the product of backside attack is formed in an Sn2 reaction here. Therefore, inversion of configuration takes place. Correct. This inversion is known as Walden inversion. This is known as Walden inversion here. So all Sn2 mechanism, all Sn2 reactions here, okay, that is, it will proceed with a backward attack. The nucleophile will attack from the backside here, and there will be inversion of configuration here. That is the nature of Sn2 mechanism here. Most important point, the stereochemistry here. Sn2 reactions, all Sn2 reactions proceed with a backside attack of the nucleophile, resulting in inversion of configuration at the stereogenic center. Okay, now this change can be observed only with a what you call the leaving group is bonded to a stereogenic center. Otherwise, it is difficult to find out all these configuration changes and all these kind of a thing. Now the other question you will ask me, why only this what you call this backside attack? Why it is not attacking from the front? It's an important point here, no? So the backside attack is preferred here. One explanation we can see, because both are negatively charged. That is, the bromide leaving group, the bromine, and the nucleophile, they are electron-rich species here. Therefore, there will be an electrostatic repulsion here. Okay, therefore energy will go up. These are the possibilities here. You see, both the nucleophile and the leaving group. Correct? Leaving group, they are electron-rich species. And therefore, when they come together, the like charges, there will be a repulsion here. So backside attack means what happens? You see, these two groups, that is the leaving group as well as the nucleophile, both are far away. They are as far away as possible. Correct? But they are not coming together here, nearby. They are far away. Backside attack. So in the transition state, we can say what happens if we draw the transition state of this reaction. There is these nucleophile and the leaving group. Both are 180 degrees apart here. Three groups here. Now we can say this is the transition state here. So the transition state of the reaction, say this is a nucleophile here. Okay, now this carbon, then we have this bromine leaving group here. So there is a partial negative charge here. There is a partial negative charge here. Then this is our D, it is there. Then R group here, methyl group. Then we have the hydrogen. Correct? So this is our transition state. So in this transition state, 180 degrees, that is the nucleophile and the bromine leaving group and the nucleophile, they are 180 degrees apart here. Okay, there is the least repulsion here and there is least energy increase here. That is, the energy doesn't go up here. Okay, around the carbon atom here. Now, if you see an example of this nature here, so this compound. So this is the as a methyl group here. Then we have a chlorine. This chlorine will be on a wedge, we can show here, and there is a hydrogen over here. So in this case, it's reacting with the OH, the nucleophile here. OH minus, it is reacting. Okay, so what will be the nature of compound? The compound formed here, it will be like this. Then this your methyl group is here only. Then OH will go behind here. Correct? Like this, plus chlorine minus. So this is the type of compound formed. That is the bond to the nucleophile. Bond to the nucleophile here. Okay, in the product, it is always on the opposite side relative to the bond to the leaving group in the static material. Okay, static material, the bond to the static material and the bond to the leaving group here. Correct? Therefore, there will be an inversion of configuration here. The bond to the nucleophile in the product, it is always on the opposite side here. Correct? Opposite side related to the bond to the leaving group in the static material. Therefore, there will be an inversion of configuration here. Inversion of configuration is occurring here. Okay, so that is the justification for the backside attack here. Now, if you see another problem, now is an Sn2 reaction here in this compound here. Okay, so carbon bromine bond is here. This bromine is a leaving group here. Then there is this hydrogen here. Okay, and say we can say there is a group here. So we can say this is a methyl group here. We can put it here, and hydrogen here. So this is a cis compound here. That is two identical groups, that is hydrogens on the same side of the ring here. Okay, so here bromine, this bromine, it is the leaving group here. So this is reacting with a nucleophile. Let us see cyanide group. So the leaving group, it is drawn above the ring on a wedge here. That is bromine and methyl group, both are on the wedge. That is above the plane of the ring, we have drawing the leaving group here. Okay, now the nucleophile, it will be attacking from behind. Okay, it will come, from the below. So what will be the nature of product formed here? It will be interesting. There will be inversion of configuration here. So the cis configuration will become trans here now. That is interesting. That is, the configuration will change. Okay, H here. Now this nucleophile Cn, it will go down below the plane of the ring here, Br minus here. That is only the CBr bond. That will be getting affected here. The rest everything will remain the same thing. There is no need to change it. You see. So this will be a wedge here. CH3 group here, same thing. Then this hydrogen below the plane of the ring here. So now the nucleophile has gone down below the plane of the ring here. So this has become a trans configuration now. Hydrogens are trans to each other now here. Okay, there is inversion. Inversion of configuration occurs at the where CBr bond here. That is carbon bromine. That's the leaving group here. Okay, the starting material is the two groups, they are cis to each other, but in the product the two groups are trans to each other here. Now the nucleophile Cn minus attacks from below the plane of the ring here. Okay, this is the mechanism generally of Sn2 reactions here. This is Sn2, that is a second order kinetics here. Okay, now Sn2. Now let us see the order of reactivity of the alkyl groups here. So the order of reactivity means I will be discussing the steric effect here. That is the rate of the reaction, how it depends upon the nature of the alkyl halide here. Okay, now the identity of the R group here. That is, we have R. That is, we have say methyl bromide or bromomethane here. Then we can have say CH3, then CH2Br we can have. Then we can have CH3 twice. Okay, CHBr. Like this, we can have different compounds here. Okay, so this will be say first thing is say methyl bromide here or bromomethane here. Then we have R. This one hydrogen is replaced by or substituted by one alkyl group here. So R CH2 Br or X here. We can say X. Okay, halide group here. So this one will be here also. I will put instead of Br, I will put it X here. CH3X. Then we have RCH2X, then we have R2CHX, then we have R3CX. Okay, now these are the primary, secondary, tertiary here. This is the, say this is the primary one, then this is the secondary one, this is the tertiary one here. Okay, now tertiary compounds do not give Sn2 reactions. Very rarely they give Sn2 reactions here. Tertiary alkyl halides, they do not undergo Sn2 reactions here. And the Sn2 reaction is fastest in the case of this compound, methyl compound, methyl bromide or methyl halides here, whatever it is there. Okay, now these compounds, secondary halides, they react more slowly here. Now methyl one and the primary. Okay, so these two, alkyl halides, they give Sn2 reactions very fast, rather. Therefore, the rate of the reaction, it will go up like this here. This is the increasing rate of Sn2 reaction. This is this order. Increasing rate of Sn2 reaction. Correct. So the reaction rate will increase in this fashion towards this direction here. So what is the explanation here? This is due to steric effect. Okay, the steric hindrance, it is caused by the bulky alkyl groups here. It will make the nucleophilic attack from the backside, because we have seen it is a backside attack here. Therefore, bulky groups attacking from backside, it becomes difficult. Okay, backside attack is becoming difficult, and therefore the reaction rate, it will come down. The reaction will slow down here due to the steric effect or steric hindrance at the carbon atom. Or unhindered alkyl halides, the reaction will be the fastest. Always it is like that. Okay, now this effect of the steric hindrance, in a Sn2 reaction, we can see it is reflected even in the transition state here. Okay, now if you just see, I can just, before concluding, I will just give you an example here. That is a transition state. So consider a reaction of this nature, say OH minus, a nucleophile. So it is reacting with the two different types of alkyl halides here. So CH3Br. Okay, so here, and another alkyl halide will be, say, CH3, we can say CHBr. Two types of alkyl halides are there. So it is reacting here with the OH minus. So what will be the nature of the transition state here? That is what we have to see now. Okay, the transition state of each Sn2 reaction, it will consist of 5 groups will be there. We know that. So I will just draw it here. Then it will be very clear for you. So there is a partial negative charge here, partial negative charge here. Correct? Then there is CH3. We are talking about CH3 here. So one hydrogen, we can put it above the plane, one below the plane here. Okay, so this is the transition state here. So it is not a crowded one. And the central carbon atom, it is not crowded here. Less crowded transition state. Therefore, the reaction will be faster here. The energy will be lower. Correct. Now, in the case of the other alkyl halide, let us see how it looks like. So OH here, then we have carbon, then bromine, then we have one CH3 group over here, then another CH3 group here, then another hydrogen, so this is the transition state, involving the other alkyl halide, nucleophilic substitution, Sn2 reactions here. Okay, so you can see the difference here. That is, in this transition state A and this transition state B, you can see the difference here at the central carbon atom here. Okay, in the B, in the transition state, it is a more crowded carbon atom here. Okay, so the higher energy, slower reaction. So bulky alkyl group, it is creating the steric effect here. Correct. Now in the first one, that is the less crowded transition state, faster reaction and lower energy here. Okay. Now the increased crowding in the transition state, makes it higher in energy. That is the energy of activation. It will go up here. Energy of activation, EA. It will go up here. Correct. So the rate of the Sn2 reaction, it will decrease. Okay. So thank you very much for listening.